In this video, we're going to look at approximating area under curves. So at this point with the material, I just kind of want to talk about something behind the scenes with the textbooks and stuff like that for right now. What we're dealing with right now is chapter 5 in volume 1 of the textbook, the OpenStax textbook, but we're also dealing with chapter 1 of volume 2 of the OpenStax textbook. So if you're in Cal 1, we're in chapter 5, and if you're in Cal 2, we're in chapter 1. So there's going to be times maybe for the next couple of chapters, if you take both Cal 1 and Cal 2 where they use web work, where you may hear these videos twice if you're in Cal 1 that finishes and then started up again in Cal 2. So you may end up hearing the same video twice because we're going to upload the same video for both sections, but just know that it addresses the same material. It's the same stuff that we're talking about. It's just going to go in two different spots because the textbook has this nice little overlap inside of it. Okay, so just know going forward, whenever we have that overlap, I'll try to mention that before videos are just like, this is section 5.1 in volume 1, this is section 1.1 in volume 2 in this case. So what we're looking at right now is approximating area between the curve that we're given, which is f of x equals x squared, and the x-axis over some given interval using 5 rectangles of equal width. So this concept of approximating area using these rectangles of equal width is what we're doing is we're finding the area of those 5 rectangles and adding them together. But when we look at the area of a rectangle, what 2 dimensions do we need in order to find the area of any given rectangle? Well, we need a height and we need a width. Okay, so we need to make sure that we can find both of these measurements for each of these 5 rectangles. But the question tells us that we want equal width rectangles, right? We want 5 of them. So what we're going to end up using is this notion of this delta x that you guys may have seen during class. But what this delta x is our change in x going from one endpoint of a rectangle to the other on the x-axis so that we have rectangles of equal width. But how can we find that width so that those rectangles are all having the same width? Like, how can we find that delta x? Well, delta x has this nice little formula for us to use, and that's a horrible delta. Let me redo that. So we have a delta, should look more like a triangle like that, is going to be given by this b minus a over n. So what this b represents is the right endpoint of our interval, this a represents the left endpoint of our interval, and the n represents the number of rectangles that we have. So for our case, what this is going to turn into is 3 minus 0 over 5, or 3 over 5. So this is our delta x for the duration of our problem. Using any approach that we use, left endpoint, right endpoint, midpoint, anything that we use, we're going to use this delta x of 3/5 because this is the width that we're going to use in order to split our interval of 0, 3 into 5 equal length rectangles. So this is what we're going to be dealing with for the duration of our problem for our delta x. So before we talk about finding the heights of our rectangles, let's look at what our interval looks like split up using this length of 3/5. So what we're going to get is we're going to get 5 subintervals that compose 0, 3, but they're going to look like this. They're each going to have a distance of 3/5, right? So we're going to go from 0 to 3/5, then we're going to have 3/5 to 6/5, then we're going to have 6/5 to 9/5, right? We're just going to kind of keep continuing this pattern for the last two. So we're going to have 9/5 to 12/5, and then lastly, our last subinterval is going to be 15/5, or no, 12/5. That should be 12. I got ahead of myself. So this should be 12/5, comma, 15/5, but that reduces to 3, right? So here we have the widths, or the kind of the start and end point of our different rectangles that we were dealing with, of our 5 equal width rectangles. And they all have a distance of 3/5. But for the sigma notations that we were given, and we'll talk about those in a little bit inside a class, we know that these left endpoints, right endpoints, and midpoints, they all have to deal with certain x's, right? So we're going to call this 0 is x naught. We have x1, x2 is going to be 6/5, x1 is going to be 3/5, and we have x3 is 9/5, x4 is 12/5, and then x5 is 3. So these are all subscripts because that's what is denoted inside of our sigma notations, is we're going to use these as reference points, right? And we'll look at those here in a second. We'll talk about a bit more about how those are represented and why those are represented the way that they are. So now that we've established our different subintervals and kind of the endpoints of them, we're going to look at how we can use those to give us the last value that we need to calculate our area, which is our height. So what we're going to do is we're going to look at this and explain this using the left endpoint method because it translates nicely to the right endpoints and the midpoints, okay? So I'm going to do is I'm going to denote that we're going to use here, we're going to use the left endpoints. But then I'm going to draw a graph of our f of x equals x squared that we have and use that to kind of talk about what we're doing. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we have 1, 1 on our graph. Here we have 2, 4. And here we have all the way up at 3, 9. So then the curve of our graph is going to look something like this. All right, looks kind of straight liney, but it's a parabola and we're going to take it as such. Okay, so when we talk about using the left endpoints, what we're going to do is we're looking to find something to deal with this variable height, right? So what we're going to do is we're going to start at this first endpoint that we have, this 0, and we're going to look for the height of this rectangle that goes from 0 to 3/5 right here, right? It says about 0 to 3/5, but using the left endpoint, what we're going to do is we're going to start there, and we're going to move vertically up the xy plane until we intersect our curve. But by the nature of f of x equals x squared, this goes through 0, 0, right? So we don't have to go up anything. So what that's telling us here is that our height for this rectangle is a big old 0. Okay, that really doesn't help us explain anything. So let me look at this 3/5 value. So here we're going to use that same type of thinking of starting at 3/5 and move vertically until we intersect with our graph. And then what we're going to do is we're going to run from 3/5 to 6/5 because that's our next subinterval, to where it's about right here. And so now we have this nice rectangle, right? We know that this width is delta x because that's what we drew it up to be for our subintervals. But then we're going to look at this height value. So this height is given to us by the function's value at 3/5. Does that make sense? Because we started at 3/5 here, and then we went up until we found the graph, right? So what this is our function's value at 3/5. And this will also give us the heights of our other rectangles. So here we went from 3/5 to 6/5 using the second interval. And now what we're going to do is we're going to go from 6/5, we're going to start there, intersect the graph, and then move over to 9/5, about right here. The reason why that rectangle looks a little bit wider than this one is just because of my scaling of the x-axis. Okay, so this is still the same delta x, but now the height of this rectangle is going to be given to us by f of 6/5, and then we go so on and so forth in this manner to find that we get the height of this rectangle, goes to here, and the height of this rectangle, we move over to 3, right? So in this interval, we went from 9/5 to 12/5, so the height of our rectangle is going to be given to us, this height is by f of 9/5. Does that make sense? Because we're trying to figure out the length of this segment, and what that is it's the distance from here to here. And that distance is given to us by f of 9/5, because we start at 0. So we go all the way up here until we hit our graph, and then we use that as our function's height. So what that means in all of our left endpoint, right endpoint, and midpoint approximations, the height of our rectangles are going to be given to us by f of x sub I. And what this I is an indexing variable in our sigma notations. And we're going to use those looking at how to more compactly denote what our approximations for the area are using the left endpoints and the right endpoints. Okay, so we have these 5 rectangles, and what we're essentially going to do is we're going to use these to approximate the area underneath this curve of x squared. In order to do that, we're going to add the area of this rectangle, this rectangle, this rectangle, this rectangle, and this rectangle all together, and that's going to give us the approximation of our area under the curve. Okay, so we say that we can approximate area by using the left endpoints of our 5 rectangles. That's what this means. The left endpoint approximation using 5 rectangles is given to us by the sigma notation of I equals 1 to 5 of f of x sub I minus 1 times delta x. Okay, so what does this mean? This sigma is a sum of these terms, right? But these terms are indexed by this I. That's why we talked about I being an indexing variable. So let's talk about how to expand the sigma notation here and kind of what that looks like in relation to what we're talking about. We talked about wanting to expand this sigma notation, but we never really talked about why we want to do that. Well, let's look inside of here and talk about what these two things are. Okay, so we said that delta x is going to be the width of our rectangle, right? It's going to be the width of all of our rectangles because we wanted to divide our interval of 0, 3 into equal subintervals with that width, right? But then this f of x sub I minus 1, we can kind of say this the same thing as this because what it's giving us is the height of these different rectangles. Okay, so what we're looking at is this is going to be the height of a rectangle, and this is going to be the width of a rectangle. But more specifically, this that we have here with this first iteration of I equals 1, what we're going to get is, let's write out what that term is going to be. So we're going to have f of x sub, and then we're going to use, since this is the first term, the first number of our index, right? So here we're going to have f of x sub I minus 1, or 1 minus 1, rather. So we're going to get f of x sub 0 times delta x, because there's nothing indexing the delta x, so we just write it as it is. So here, this first term, what we're doing is we're taking our index variable and subtracting 1 from it to talk about which x we're referring to. And in this case, we're talking about 0, right? Because we said that x sub 0 was 0 itself, and that was our first left endpoint rectangle that we used. Okay, does that kind of make sense? So what we're doing is, by using the sigma notation, is we're writing what we're going to write here in this next step, this all expanded out stuff that we're going to have. We're going to be able to write it in such a way that is more compact and cleaner to use that we can use moving forward. But for the time being, we're going to actually expand this out and look at what these values are going to return for us. So f of x sub 0 is going to be the height of our first rectangle, and delta x is going to be the width of the rectangle, right? But now let's look at our second iteration. So here, we're going to have f of x sub 2 minus 1, right? Because we used our first iteration. Now I need to look at the second one. So we have I equals 2. So f of x sub 2 minus 1 is going to give us f of x sub 1, right? And again, still multiplied by delta x. But we talked about how x sub 1 is 3/5. Okay, and this was our second left endpoint that we talked about for our second rectangle, right? So we have this one here. So naturally what's going to keep happening is we're going to look at our third left endpoint, our fourth left endpoint, and our fifth one with the other three terms that we're going to write here. So let's keep writing those down. So here we're going to get this similarly, then we're going to get this, and lastly f of x sub 4 times delta x. So like that, right? We talked about x sub 2 is 6/5, right? X sub 3 was 9/5, and x sub 4 was 12/5, right? So what we're going to do now to find our function's value is to translate these things, these f of values, because we already know what delta x is. What we're going to do is we're going to plug these x values into our function to give us these values so we can figure out the area of the first rectangle, the second rectangle, the third, fourth, and the fifth, then add them together to get the area that they all occupy together to give us a left endpoint approximation of our area under this curve. Okay, so this is what we're going to do here. We're going to plug in 0 into our function, and we saw our function was x squared, right? So we have this going on. So we're going to plug in the x value into x squared. But 0 squared is 0, right? Then we said that delta x is 3/5. So we have that going on. But we know that when we evaluate 0 times anything, it gives us 0, right? So we can kind of save our space on that one for the next step that we have. But let's continue evaluating the different heights of these rectangles to figure out what they are. So here we're going to have 3/5, or f of 3/5 rather, is 3/5 squared. So that gives us 9/25 times 3/5, the width of our rectangle. Then here we're going to have 6/5 squared times delta x, which that turns into 36/25 times 3/5. Then the next term we're going to have is 81/25 times 3/5. And then our last height of our rectangle here is 12/5 squared, which gives us 144/25 times 3/5. So we have this going on. So now let's multiply these together so that we can add all the fractions together and see what our approximation is for our area under the curve using the left endpoints. So here we're going to multiply these things together. We're going to get 27/125. Then we're going to add that to 108/125. And then we have 243/125. And then we're going to have 144 times 3 gives us 432/125. Adding these all together, we get 810/125, which simplifies to 162/25. So this is the approximation of our area using rectangles constructed with left endpoints that have the equal width of each other, right? They have the same width, but we used the left endpoints to approximate, or to find their heights of the rectangles, and then we use those to find the area of each rectangle, which we had here. and then we added them together to approximate the area that those rectangles occupy to give us an approximation of the area underneath this curve x squared, but above the x-axis. So that's what we were doing there. Well, now let's look at the right endpoint approximation. The process is largely the same, except this changes a little bit, our formula that we use in here, because instead of using these left endpoints, we're going to use our right endpoints here, right? So what we're going to do is we're going to get some different looking rectangles. So let's go ahead and I'm going to go ahead and erase what we had under here, kind of, sort of, just so we can kind of clear out what we have, and I'll reconstruct it because we're going to use a lot of the same stuff here. So here we had our curvature that looked like that. And this all kind of goes away. So now let's redraw our x-axis as best we can. And we have this. So we had this was 1, 1, was right here. And then 2, 4 was right here. And then 3, 9 was right there. Okay. So what we're going to do first is we're going to redraw our rectangles, but this time using the right endpoints. Okay, so we're using that same strategy of starting at our endpoint value and going up until we hit the graph to find our function's value at that point to give us our height. That's still not going to change, right? So this is f of 3 in this case, right? Then we're going to move to the left horizontally 3/5 till about right here. So it's still going to be delta x. And this is going to be our first rectangle, right? Then our second rectangle is going to be, since this is 12/5 right here, we're going to find that our rectangle intersects right here on this graph. So this height is going to be f of 12/5, and then we're going to move over a factor of delta x. So where we get this rectangle, and then for our next rectangle we get something like this because our next right endpoint is 9/5. We go to the left until we hit 6/5. This is our next rectangle. Then we use our right endpoint of 6/5, move over to 3/5 right there, and then we use 3/5 to make our last rectangle, which is right here. All right, so here we have our 5 rectangles again, but now we're just going to be dealing with different height values, right? We're going to have some in common that we use with the left approximation, but we're going to have some different ones in there too, right? So what we're going to need to do is we're going to need to alter this approximation formula a little bit, because just as like area can be approximated with the left endpoint formula, we're going to use this same thinking of a sigma notation, but we're going to change something inside of here. So I'm going to scroll down here a little bit, and I'm going to rewrite what we have as our approximation for this guy. So here, we're going to approximate area, approximate, with the right endpoint approximation, r sub 5, because we're still dealing with 5 rectangles, right? So this is going to equal the sigma notation, again, still going from 1 to 5, that's not going to change. What's going to change is the f of x term inside of our notation, right? Because when we look at what we were doing to make our rectangles, we started here with this first right endpoint rectangle was made. This was made with x sub 1, right? And this was made with x sub 2, this was made with x sub 3, x sub 4, and x sub 5, right? So we were not using x sub 0 like we did, which is why we use that I minus 1 in our subscript there. What we're actually going to use is this time just f of x sub I times delta x. And again, the reason for that is because we started with our first right endpoint rectangle was right here at x sub 1, right? So we want our first iteration of the sequence to be 1. We want to go up to 5. So we have this going on here, right? Does that kind of make sense? So that's why we have a difference between the right endpoint approximation and the left endpoint approximation. So what we're going to do now is use largely the same strategy that we did over here. We're going to expand out this sigma notation to see what we get in here, and then use that to figure out what our right endpoint approximation is. So again, I'm going to go ahead and write out our f of x terms just so we have a visual of what we're dealing with. So here we're going to have f of x sub 1 delta x plus f of x sub 2 delta x plus f of x sub 3 delta x. And then keep in mind, when we're talking about these different f of x sub whatever values, those are the heights of our rectangles, and then the delta x is going to be our width of the rectangles, right? Because our delta x is always 3/5, that's how we made it to be. We always made it to be this width of the rectangle. But then our f of x values give us the height of the rectangles that we have here. So here, our x sub 1 is 3/5, x sub 2 is 6/5, this was 9/5 for x sub 3, 12/5, and 3, right? So now what we're going to do is, again, using the fact that our function is x squared, we're going to square each of these x terms to find out our function's value at those points, multiply them by delta x, and then add those products together to give us the area of our rectangles that we drew in our picture to approximate the area underneath our curve. Okay, so like I said, let's go ahead and square these values, multiply them by delta x, and let's figure out what the area of our rectangles are added together to get us our right endpoint approximation. So again, 3/5 squared gives us 9 over 25. That should be a fraction there. And this is times 3/5 again, because delta x is 3/5. Then here we're going to get 36 over 25 times 3/5, plus 81 over 25 times 3/5, plus 144 over 25, which is 3/5, or times 3/5 rather, and then plus 9 times 3/5. Okay, so let's multiply these together and then add them up. So here we get, again, 27 over 125. So like I said, there's some similarities here between the left endpoint approximation that we did, so I'm going to copy those values down that we have, because those multiplications are repeated. So here we get 143, this is actually 243 rather, and this is 125 plus 432 over 125 plus 27 over 5. But to make this have a common denominator to be able to add these together, I got to multiply both the top and the bottom of this fraction by 25 over 5, or 25 over 25 rather, right? So what I'm going to do is I'm going to add these together, all these that we had here, because we know that from what we had just earlier, this is all 810 over 125, but then we're going to add this in with its new common denominator, and that's going to give us 675 over 125, and if we add those together, we get 1485 over 125, which reduces to 297 over 25. And this is the right endpoint approximation of our area that we just talked about being underneath the x squared curve. Okay, so we've talked about the left endpoint approximation and the right endpoint approximation. They're both kind of the same in what we do. We construct rectangles using either a left or a right endpoint, but therein lies the difference right there. We either use the left endpoint or the right endpoint, right? So we talked about the left endpoint and the right endpoint. Let's look now at constructing the approximation using the midpoints. Okay, this is going to be one that's going to be a little bit interesting. Okay, so what I'm going to do is I'm actually going to scroll back up and over so that I have my subintervals in the window. Because what we're going to do is we want to use the midpoint approximations of these. So like how we use the left endpoint and the right endpoint, what we're going to do now is we're going to split these in half and figure out the midpoint between these and then use those to construct our rectangles. Okay, so what I'm going to do is I'm going to rewrite these over here where we have a little bit more room. What I'm going to do out beside them is find the midpoints between these two endpoints here so that I know where I'm constructing, or what x values I'm using to start constructing my rectangles. Okay, so the midpoint between 0 and 3/5 is going to be basically cutting 3/5 in half, right? So let me scroll up a little bit and denote that. So here what we're going to have is midpoints right here. So this is going to be 3 over 10, right? Because if we increment this to 6 over 10 by making an equivalent fraction, half of 6 over 10 is 3/10, right? So what we're essentially going to end up doing is we're going to add 3/10 to our left endpoint and on each of these to give us the midpoint of these two, because if 3/10 cut 0 to 3/5 in half, adding 3/10 to this, and this will give us the midpoint between those two. Okay, so if we add 3/10 to 6/10, here we get 9/10. And all I'm doing kind of in my head is making these equivalent fractions and adding them together, right? So if I need to put 6 over 10, I need to make sure I increment 6 to 12. 12 over 10 plus 3 over 10 gives me 15 over 10, right? And then here we would have not 9 over 5, but 18 over 10 plus 3 over 10 gives me 21 over 10. And then here, 12 over 5 becomes 24 over 10 by making an equivalent fraction, and so we get 27 over 10. Okay, we're going to redraw our function f of x and then use these midpoints to construct rectangles and use the same thinking that we did with the left endpoint and the right endpoint and using a sigma notation to approximate our area under the curve y equals x squared. So now that we found our midpoints, let's go ahead and redraw our graph so that we can see what we're dealing with here. And so we're going to have this 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. I kind of redid that even though it really didn't need to happen. I'm just being picky with the details now. So let's go ahead and replot this curve. So 1, 1, 2, 4, and 3, 9. So we get something that looks like that. Okay, so what we're going to do now is we're going to use that same type of strategy that we use with the left and right endpoints, but by plotting our midpoints on the curve of the graph and drawing the rectangles. So what we're going to do is we said that the midpoint between 0 and 3/5 was 310, but what we're going to do is we're going to use a rectangle to cover that same subinterval of 0 to 3/5. Okay, so instead of how like the left endpoint triangle went all the way to the right, what we're going to do is we're going to use this midpoint, and we're going to move to the right 3/10 and to the left 3/10 to cover our original subintervals. Does that make sense? So every time we use one of these midpoints, we're going to construct the rectangle that starts here, and then we're going to go back to our left endpoint of the subinterval and then go over to the right endpoint of the subinterval. So we're still going to have this factor of delta x being our width here, but what we're doing instead is we've made these midpoint rectangles so that we kind of have a nicer approximation, right? Because here we have like this over approximation of this curve, and here we have a little bit of an under right here. And then if we draw this rectangle, we see that same thing. Right? With all these, we have a little bit of an over approximation, and then we also compensate for that in a way by also having an under compensation too, right? So we get this goes all the way to that. So like how we do with the left and the right endpoints, we saw that with the left endpoints, there's a very big under approximation of our curve, and then the right endpoints had a big over approximation. This midpoint kind of takes the best of both worlds and does both at the same time, to where we hope they kind of sort of cancel out, but if they don't cancel out perfectly, which they really won't, what's going to happen is it's going to give us a better approximation of the area underneath our curve, or the area between our curve and the x-axis rather, here, okay? So just like we denoted these as x sub whatevers, I'm going to call these, where this is midpoint 1, midpoint 2, midpoint 3, midpoint 4, midpoint 5, if we wanted to use them inside of a sigma notation. But since what we've been doing up to this point is just using that sigma notation to expand it and write it out, what I'm going to do is I'm going to skip the sigma notation part and say that our area can be approximated as these different function values to give us the heights of our rectangles, and then using that same delta x factor multiplied to each one of them, right? Because the width of the rectangle is still delta x, but now the height of our rectangle is going to be given to us by f of midpoints. Okay, so f of midpoint 1, 2, 3, 4, 5 is going to give us the height of this rectangle, then this, then this, then this, then this. We're still going to multiply each of those function values by delta x to give us the area of each individual rectangle. Then we're going to add them together. Okay, so this first rectangle is given to us by f of 3/10 times 3/5, right? F of 3/10 gives us the height, 3/5 gives us the width. So then here we have f of 9/10 times 3/5. Then here we have f of 15/10 times 3/5. Then we have f of 21/10 times 3/5. And then lastly, our last rectangle is given to us by the dimensions of f of 27/10 times 3/5. So now what we're going to do is, again, using the fact that f of x is x squared, we're just going to square these values inside of the f of expressions, then multiply them by the 3/5, or the width of the rectangles, to give us the area of each individual rectangle. So then this is going to be 3/10 is going to give us 9/100 times 3/5 plus 81/100 times 3/5 plus, and then 15 squared is going to be 225/100 times 3/5, And then we get 21 squared is going to give us 441 over 100 times 3/5. And then we're going to add 27 over 10 squared, which is going to give us 729 over 100 times 3/5. So every time I was saying just the numerator squared, I was meaning to say that we're going to square the whole fraction. That's what I've been meaning this whole video. But we already know kind of by easy math that 10 times 10 is 100, so 10 squared is 100. Okay, so now let's take care of finding these products and add them together to give us the approximation by using the midpoints. So what we get for this first product is 27 over 500 plus 81 times 3 gives us 243, and that's over 500, plus 225 times 3 gives us 675 over 100. And then we're going to add 441 times 3, which gives us 1323 over 500. And this is going to be a 5. That was my fault. Plus 729 times 3 is 2,187, again over 500. Okay, so then adding all these numbers together, we get 4,455 over 500. Okay, and then we can simplify this to give us 891 over 100. And this is our midpoint approximation of the area between the curve f of x equals x squared and our x-axis. Okay, so looking at the three methods kind of in comparison, we did here, the last one we did was the midpoints, and then the first one we did was the left endpoints, and then we also took care of the right endpoints, right? So we've looked at all three of them, and we saw that we got different values for each one because our rectangles were made differently, right? Our left endpoints gave us an underestimation, our right endpoints gave us an overestimation, and then we can kind of maybe say that our midpoints gave us the best approximation, but we don't really know for certain, right? Because these are all approximations, so who's to say? But we saw by the way that we drew the rectangles that that's kind of where we led to our conclusion, okay? So just kind of as a little bit of a recap, when we talk about finding the area between a curve and the x-axis by using rectangles, we have to figure out what our delta x factor is, or the width of our rectangles, and then use that to figure out what our left and right endpoints are, and then also in a way to figure out what our midpoints are, kind of, sort of, because if we wanted to, we could have just cut this in half, this delta x, to figure out what our midpoints were, but by keeping this delta x preserved, we could still use it as our delta x inside of our calculations. So if we would have cut 3/5 in half, we'd have found that'd be 3/10. So then we could cut each of these intervals down the middle by finding 0 plus 3/10, 3/5, and 3/10 like we did. Okay? So when we do all those, we just need to keep in mind how we draw our rectangles using the left endpoints and the right endpoints, and then keeping in mind the sigma notation, which endpoint we start with. Like we start with f of x0 here, and then with the right endpoint approximation, we start with f of x1, right? Because our right rectangle starts with x1, and then we go over here. Our left endpoint approximation starts with our first endpoint, moves over here, and excludes this x sub 5, right? But our right endpoint approximation excludes x sub 0. So that's kind of how we can think about that there, okay? But just kind of going forward, we have these three methods in our pocket, and we know how to use them now to approximate area under curves.